Today we're going to continue the discussion of comparing data in our sets and how to describe the differences between the two and which type of data we want to use to describe the population that we have. But specifically today we're going to discuss something called a linear transformation, which is, as it states here, an operation performed on that data set that can be written as a linear function. So a linear function is y equals mx plus b, where we take and multiply a value by a constant or add something to a value. So in this case, we're going to look at two things today. One, when a number is added to a data set, or when a number is multiplied to a data set. When I say added or multiplied, I'm talking about to every term in that data set. So here's our first question of the day. We want to take and find the mean, median, mode, range, standard deviation of each of the two sets I have here. So what I've done is I've got a set of 4, 6, 8, 13, 17, and then I add 5 to each number in that set, giving me these new numbers. And a lot of this we can do just by looking at it. In fact, let's go ahead and write a little chart here. We have the mean, the median, mode, range, and standard deviation for each of these sets. So in this case, I'm going to have to calculate that. Median here is going to be 8. Mode is none. I'll just go to no solution. Range, I take the difference of 17 and 4, which is 13. Standard deviation I'll have to calculate. Over here we're going to take, again, and calculate the average. The median, in this case, is the middle number, or 13, since I only have 5 numbers. There's no mode. My range, again, I'm going to subtract the high from the low, get a total of 13, and standard deviation I'll have to take into account. So let's go to our calculator, and in our calculator we'll go to stat and edit, and you'll see that I plugged those values in. You can do that right now. Next I'll take and I'll calculate some one variable statistics so we can get a standard deviation. So let's go ahead and do that. Quit, and then go to stat, calculate those one variable statistics, and we'll do it for the first list. So I'll go second, get L1 up there and hit enter. So here we have our average and our standard deviation. In this case, we've got an average of 9.6 with a standard deviation of roughly 4.76. Now we'll go back and again calculate our one variable statistics for the second list. So second L2, and here's our average of 14.6 and a standard deviation of 4.76 again. And you'll notice right off the bat that the average differs by 5, our median differs by 5, we have no mode for each, but our range in this case is the same as is our standard deviation. And if you think about it, that makes a lot of sense, because if I've added 5 to each number, my average should go up by 5. My median, my middle number, should go up by 5. The range is a difference between the high and the low, and if the difference was 13 to begin with and I add 5 to each number, I still have a difference of 13. And a standard deviation talks about the grouping or the average distance away from the average of the data set. So again, if I add 5 to both, my grouping is still going to be relatively the same. So this is kind of big. In essence, if we have a transformation of an addition, in other words, we add a number to every value in the data set, the mean, median, and mode of the new data set can be found by adding whatever k value we add to each portion of the set of data, but the range and the standard deviation won't change. So next what we're going to do is we're going to take and find the mean, median, mode, range, and standard deviation for this data set here, which is the same as the last. But instead of adding 5, I'm going to multiply each term by 5, and we'll see what happens to these 5 values from here. So let's once again go back to our list. I've typed in my new L2 list of multiples of 5 of the beginning set of data, and I'll once again quit, and we're going to calculate our one variable statistics on L1. Once again, we get those same values of the average being at 9.6, our median was at 8, no mode. We had a range of 13 and a standard deviation of 4.76. Now we'll go ahead and calculate all that information for our second data set. So we go stat, calculate, one variable statistics for L2, and get our new values. And you'll notice in this case, our average is 47. We've got a median, in this case of 40. Still no mode. We take the high minus the low. That gives us our range, 65. And then our standard deviation was 22.25. And again, you notice that in this case, each of these differ by our initial set by a multiple of 5. So again, that's a pretty big deal. We have a transformation on a data set where we take and multiply every term in that data set by a constant k, where k is greater than 0. The mean, median, mode, range, and standard deviation of every value for that new data set is all multiplied by 5. So let's now compare some data. We've got a set where Brittany scores a certain amount of values on a computer game and Justin scores these values, and we want to take a look at a histogram on our graphing calculator and then describe the shape. So I'm going to let you plug these numbers in, graph the histogram, and then we'll talk about what we get. You might want to pause. So what I did is I plugged all this in and I made my X scale to go from 25 to 60, and I made my scale factor by 5, and this is the graph I got out, and my Y's went from 0 to 8. Justin ended up looking like this. So you'll see that this is a pretty evenly distributed set of data, or a symmetric set of data, and this is skewed definitely where we have more numbers on this side. So we say this is actually positively skewed. Alright? So for Brittany's scores, once again, distribution's high in the middle, low on both sides, so that's symmetric distribution. For Justin, the distribution's high on the left, low on the right, so it is skewed positively. If we take and use those same scores and using either a standard deviation or a 5-number summary, talk about how those differ. Once again, going back, since we have one that is symmetric in nature and one that is skewed in nature, we want to take and use that 5-number summary or that box and whisker plot to compare our data. So given that we're using a box and whisker plot, we're going to be comparing medians and quartiles and see where the bulk of the data lies. So go ahead and on each of that set of data, go ahead and calculate one variable statistics for both, noting your median and your quartiles. And this is what you should end up with. Since that one distribution was symmetric and the other was skewed, once again we use the 5-number summary or box and whisker plot to compare. We noticed that both distributions had a max value of 58, and Brittany's score had a minimum of 29 compared to Justin's minimum of 26. The median for Brittany we found was 43.5, and the upper quartile for Justin was 43.5, which means that 50% of Brittany's scores, in a sense, were between 43.5 and 58, while only 25% of Justin's scores fell in between that same range. So we conclude overall that Brittany's scores were actually higher than Justin's. And again, if we look at the box and whisker plot itself, we can easily tell that. Let's do that. And again, if you want to compare two box and whisker plots on the same plot, you have to turn two plots on. So here I am in stat plot. If I move down to my second plot, I'll hit enter and I'll turn that plot on. I move down to the type of plot, and again I want a box and whisker. Hit that. I'm going to use the following window of 20 to 60 since my scores are between those two. And you'll notice that I've got a scale of 3 and a y min of -5 and an x max or a y max of 10. All right. And then the other thing we're going to have to do in that stat plot is make sure you tell them in window 2 that you're using values from list 2 to make that plot. So I'm going to have to change L1 to L2. Then I go ahead and graph, and you'll notice here are my two sets of values. And as we were talking before, we said that Brittany's, most of her scores were higher than Justin's, and you can see that in the box and whisker pretty easily, because we see that 75% of all Brittany's scores are from this low point here out to this high point, even though the two high points are the same, while 75% of Justin's scores only reach the median value of Brittany's scores. So really Brittany's probably the better player. Next we're going to do the same for another set of data where we have guys who are fishing. They catch a number of fish in a day. We got Steve and Kurt, and we're going to compare what they've done with a box and whisker plot instead of a histogram, and then use that data to describe what's going on. So after plugging into my stat plot and finding our box and whisker plots, we see we have two sets of data. In the first case, we see that one guy catches a heavier fish than the other, and in general, both box and whiskers seem to be pretty evenly distributed. And since each are evenly distributed box and whiskers, we would use the mean and the standard deviation to basically describe their data and make comparisons. So in this case, if I find standard deviation of the first and the mean, the first is going to be x bar is equal to 2.5, and the standard deviation is equal to 0.8. And again, you use your one variable statistics to do that. For the second set of information, we get an average of 2.7 and a standard deviation of 1. So what that basically means, like I said, since this second guy had a couple heavier fish, his average went up. But you'll also notice his standard deviation is greater, which means there's more variability from the mean in the fish that he catches. So in terms of comparing the two, we can say that this guy is actually catching closer to his mean than this guy. And a written out response of this would be as follows. The distributions are symmetric. Mean and the standard deviation are used to compare the data since that distribution is symmetric. The mean weight for Steve was 2.5. The standard deviation was about 0.8. Mean weight for Kurt was about 2.7. Standard deviation 1, as I just stated. And while the mean of Kurt's fish was greater, the weights of Kurt's fish, since he had a higher standard deviation, had more variability, which means that Steve's fish were generally closer to his mean than Kurt's. So again, we just talked a little bit about how to describe data. The big deal about comparing the two was if we had a skewed distribution, we use a box and whisker or the mean and the ranges of the quartiles, whereas if we had a symmetric distribution, we use standard deviation and a mean rather than the median. Here are a couple of questions to answer based on what we did today. There's your first guy. Here's your second. Write your lesson summary, and we'll chat more tomorrow.